Okay, next up, we're going to have Paul and Paul Horwitz. And actually, Paul, you said you wanted to introduce yourself, right? Do you want me to leave this slide up?
Okay, let me share my screen. You can read this stuff, but you don't really need to. Yeah, I'm going to say continue, and I'm going to try to find my screen. Let's see. That's not the screen I want. Maybe that might be better. How about this? Okay, I'm not sure what you guys are seeing. Are you seeing my, are you seeing two screens at once or just one?
We are seeing your presenter view, right? That we see your slide and your next slide.
Okay, you're seeing what I'm seeing on this monitor. Well, never mind. You can see both slides. Who cares? Okay, so I want to go quickly because I don't have a lot of time. Let me move on to the next slide. There we go. First of all, this is going to be somewhat odd and different from some of the other talks in that it's not an actual project yet. It's just a proposal. We wrote a proposal, Jay and I, and some others, which just got submitted to the National Science Foundation in October 1st. And for some reason, they haven't yet funded it. I can't understand it, but hopefully they will. If and when they do, the audience is going to be high school computer science or physics classes. And the goal is, as you can see, to introduce quantum computing, but really without a lot of math. Quantum computing, let's start with the fact that quantum computing is a thing. It's going to be a thing. It's already a thing. It's going to be more of a thing. Sooner or later, there are going to be quantum computers that actually work and that people can use. And NSF is interested in the whole question of to what extent can we, since we've now created digital natives in some sense, now can we create quantum natives? Can we create kids who can think sort of quantum mechanically and understand the quantum algorithms that are at the basis of quantum computing? So we're not teaching the algorithms themselves. What we're teaching is, and just in fact, having two screens at once is interesting, but wasn't intended. The whole question here is, can we teach kids with basically no math the bizarre quantum mechanical phenomena that underlie quantum computing? Because quantum computing is really different from classical anything. Quantum mechanics is peculiar. And what we're going to do is we're going to create what amounts to a cognitive on-ramp by starting with some colored cards, and you can see them on the left here. They have 3 stripes, and the stripes can be either blue or red. So 2 to the 3 is 8. There are 8 different kinds of cards, either all blue or all red or some blue and some red and so forth. We will put them into the box that's on the right. It's a poorly drawn box, which is an opaque box with a slit in it so you can slide the card in face up, and a kind of a dial at the top that you can turn and then open up. So you're looking at only one stripe at a time. Okay, so you're only going to measure along one angle, either vertical, let's say up and down, or slanted to the left or slanted to the right. And each time you're going to get a red or a blue. And because it's a card, and plain old classical card, if you measure 3 different times in 3 different directions, you're going to know what card it is. And we have some activities about how likely is it to be this other card or what have you. I'm not going to go into that in great detail, because the point is that that's not what happens with qubits. Qubits are different. First of all, well, I'll get to how we talk about the qubits. How do we make qubits? But a qubit, think of a photon. Don't think of a photon if you have no idea what a photon is, but think of a thing which is quantum mechanical and somehow is in one or the other of these 2 states. Let's call them red or blue. They could be spin up or spin down. They could be 1 or 0. It doesn't much matter. 2 different states. And they can be measured in, let's say, 3 different ways. They can actually be measured infinite number of ways, all different angles, but those 3. And with qubits, when you take the first measurement, you're going to see red, you're going to see blue, and it doesn't make any difference. It's 50-50. If you make a second measurement, the angle that you get is going to depend on how big an angle you made between the first measurement and the second one. So if you make a small angle, you're more likely to see the same color. If you make a bigger angle, you're more likely to see the other color. That's not all that bizarre. It's a little bit bizarre, but it can be mocked up in a classical way, almost. But the key thing is when you go back to measuring the first thing you measured, you may not see the same color. Because in quantum mechanics, and you guys have all heard of Heisenberg and uncertainty and all that stuff, when you make a measurement on something that's quantum mechanical, you affect the thing. The measurement itself affects the thing. And the second measurement may very well not be the same as the first. Okay, so that's a qubit. It's different from a card. How do we make a qubit in the classroom? After all, these things are made in physics laboratories with lots of money and lots of PhDs, and they're hard to do. Imagine then that we have cards, but instead of stripes on them, they've got a QR code. They've got this thing that a computer can scan. Okay, we all know what a QR code is. That's that funny thing that you scan. Okay, or it could be a barcode. It doesn't much matter. But the computer can scan that thing, and then on the screen of the computer, imagine that you've got something that looks like that little box that I showed. And when you scan the card, the box disappears, and up pops a color, a bar, just as though it were a card, as though you had opened up the thing and you looked at the card. Okay, so it looks very much like the card, except it is a card. It's an actual real card that's being scanned by a computer instead of being put inside a box. Okay, now the cards are going to simulate the qubits. So with the cards, you're not going to get the same behavior that you had with the cards. And believe me, we've worked out a situation where it will be clear, we hope, to the kids that there's something very bizarre going on because these quards, we call them, these quantum cards, are behaving differently. Okay, fine. Last slide. What does all this have to do with quantum computing, which after all is the subject of the talk, right? Well, it turned, and I'm not going to be able to go into this in great detail, but it turns out that because you can entangle quards, and I haven't explained what that is, but I will now in a way. I'm doing a lightning thing here. I don't expect everybody who haven't heard these things before to really know exactly what I'm talking about. But if you entangle two quards, for example, now when you make a measurement on the two quards are one thing quantum mechanically, even though they may be separate, they may be in different classrooms, different schools, whatever. It doesn't matter. There's one thing quantum mechanically. And when you make a measurement on one of them, it's as though you made a measurement on a qubit, except it's a double qubit. So it affects the measurement of the other one. So Alice and Bob, Alice makes a measurement, sees a red stripe, and now, depending on what measurement Bob makes, Bob is more or less likely to see a blue stripe or a red stripe, depending on whether, or the same color, if it's the same direction. Exactly the way repeated measurements happen with a single card. That is very bizarre, and it turns out to be not reproducible at all classically, but you can reproduce it in the laboratory. And now what I'm going to tell you, and you have to take my word for it, that this has huge implications for being able to solve certain kinds of problems faster, considerably faster than can be done classically. And I haven't explained why that happens. And as I mentioned before, the curriculum we're talking about here that hasn't yet been funded would not go into great detail about the algorithms for quantum computing. Rather, we're trying to get kids to be quantum literate so that if they ever do encounter quantum computing, they will understand the underlying physics. Okay, that's what we're doing. It hasn't happened yet, and I apologize for the fact that it isn't exactly on the topic of the rest of the talks because we haven't yet been funded, but now that we all know about it, maybe we will be. Thanks a lot.
Cool. Thank you so much, Paul. Yeah, I look forward to seeing more about that